We're here. And you're being recorded. If you didn't hear that, the session is being recorded and will be available afterwards. Welcome to today's session, Novel Approach in Seasonal Snow, Field Measurements, Remote Sensing, Modeling, and Data Assimilation and Analytics, Part 1. So we have two other sessions, just for your awareness, later today at 12:55 local time and then at 2:55 local time, Part 2 and 3 of the same session. I'd like to thank the co-conveners for this session, Inseng Cho, Melissa Reason, Kerry Vujovic, all from NASA, and also our colleagues in the ESC Executive Committee that helped coordinate this with CGU and CMOS, Craig Smith and Chris Chutko. So thank you all. So without further ado, I'll just say each presentation is scheduled for 15 minutes. If you could, I'll try to keep the time for you, and then maybe just chime in when there's a few minutes left, just so that we'll have time for a question or two. We've got two poster presentations, which are only 10 minutes. And I'll just point out to both Andres and Angela, it may be the order of those are Andres and then Angela, which might be different than what you saw earlier. So at 9:10, Andres is a slot, and then 9:15, Angela's slot. So I'll just alert you to that before your presentation, so you know you're next up. Okay, first up, without further ado, is Ed Kim, and his presentation is Advances in X and KU band radar algorithms for SWE retrieval by future satellite missions. And I'll be driving the slides for that. So I'll bring those up for you, Ed.
Okay. Thanks, everybody. I'd like to acknowledge my co-authors. You can see DK Kang at Goddard and Faraz Bora and Lung Sang from University of Michigan. It's, if we could go to the next slide, please. So I'll just briefly give some background, some motivation for a global snow mission, but focus the majority of the talk on a short description of the algorithm itself, and then really focus a little bit more time on validation, where I think there's been a lot of advance since, let's say, over the last 10 years or so, and then wrap up with a summary. Next slide, please. All right, for this audience, I don't have to go over the importance of snow, but it has been also recognized at the level of the National Academy in the US through the decadal survey recently completed around 2017. And they identified 7 geophysical observables, one of which was snow water equivalent for potential deployment in a future satellite mission. That doesn't mean that all 7 will turn into satellite missions. In fact, that group of 7 was recommended to be a competition. So a group of us within the community are working towards a mission concept, keeping in mind, as many of you have found in your own work, and also through the literature, that there's no magic bullet technique that measures SWE under all conditions on the planet. So we're really looking at trying to find a combination of techniques, one of which offers certain advantages is synthetic aperture radar, and specifically the technique that I'll be describing today is using SAR at X and KU bands, where volume scattering is the physical mechanism that's giving us the signal. And as I mentioned at the start, the focus of this paper is really on describing the latest work on the algorithm, as well as the validation work that goes along with that. So next slide, please. This slide's a little dense. You can ignore for the moment the 2 boxes at the bottom. Those are references that you can look at your leisure. But this approach really relies on looking at the difference between the volume scattering at these 2 different frequencies. And it's based on a physical model, the dense medium radiative transfer model, which also incorporates a representation of the sort of snow air matrix known as a bicontinuous model. So this bicontinuous dense medium radiated transfer model is the physical basis. And that, as some of you may be familiar, is a fairly complex model, involves a lot of input parameters. And one of the key advances for this algorithm in the context of this mission has been the development of parameterization of this that greatly simplifies how you use the model and greatly reduces the number of input parameters that are needed. So it really boils down to a two-parameter retrieval. There are two unknowns, one of which is SWE, and the other is, in the case of this representation, the single scattering albedo, which we represent with that omega variable. And that's really the fraction of the attenuation of the radar signal that comes from scattering. So we've got two unknowns, and we have two observations using the VV copole backscatter measurements at both X and KU bands. We subtract out the contributions of surface scattering. So this is the scattering caused by the ground surface at the snow-ground interface that doesn't really contain any information about the amount of SWE that's present. So you subtract that out, and that leaves the volume scattering signal, which contains your SWE information. You've got two unknowns and two observations, and we use a cost function approach, which is shown in that equation in the box, sort of midway down the slide there. And this relies on modeling. There are two solutions, as we found. And these two solutions, so the solution space sort of groups itself into two clumps, and that those two solutions are correspond to two different values for that albedo parameter, the omega variable. So we need an initial guess, either in the high or the low albedo range. So albedo can range between 0 and 1. So either you either use a 0.35 or 0.365 initial guess, and that allows the cost function to home in on the correct solution. Next slide, please. So we mentioned the surface scattering subtraction. That's very important, and that estimate is based on, again, electromagnetic theory, full wave simulations that have been converted into a lookup table, along with formulations that are consistent with theory from O, and this has been compared and validated against tower data from field measurements. We've got a number of sources of input data for this, including snow-free observations that you would get from the same radar that would be observing the SWE a little bit later in the year. Passive microwave is another potential source. Using anything that can give you an idea of the height, or rather the roughness of the surface. For example, there is a roughness product from the SMAP mission. And you can also get this from other L and C band radar observations, along with frequency scaling relationships that are well established in microwave theory. So these different options are being evaluated. And I mentioned that you also need this initial guess for the second parameter, the omega. You don't really need a very high fidelity guess because the omega turns out to be effectively a two-valued variable. And we even tried an experiment where we intentionally used the wrong guess, and you still get a reasonable SWE retrieval. Next slide, please. So the algorithm may sound, a little bit complicated. It's actually very, much simpler and more practical than previous algorithms over the past 10 years that have relied on that same volume scattering. And I think one of the key advances in this case now has been the effort to validate this approach. And so this slide just lists a number of different airborne data sets that are available for validation. And the two in green are ones that have where we've completed using those particular data sets. And then you see a couple other ones marked over in that left-hand column as being under study. So those additional 3 data sets are being used right now. There's validation efforts in progress right now to use those field data for validating this algorithm. And on the next slide, you'll see a list of tower data sets, and 2 of those have also been used to validate the algorithm. So these give us validations over different regimes of how much SWE there is and under different conditions around the world. On the next slide, you can see well, okay, so I figured I'd better put a few pictures in here and not just fill all the slides with text. So back in 2017, during SnowX, we flew the SnowSAR sensor from ESA on the P3 aircraft in that top left picture. And so that's been one of the key data sources for validation coming from airborne field measurements. And next slide, please. The validation also, I think you have to click it a few times to get the rest of the pictures to show up. Yeah, keep going. There we go. So in addition to the remote sensing observations, whether it's airborne or tower-based, you also need ground truth. And there's some photos of our colleagues at work collecting ground truth. Next slide, please. So if you take the three different airborne data sets that we've got, the 2 on the left are complete validation exercises, complete. The one on the right, that's almost complete. But we've got validation now over different SWE regimes, different snowpack types, and so forth, that show fairly nice performance for the algorithm. This is really comforting to see, especially for a radar algorithm, that it seems to work over very different snowpacks. Next slide, please. And the same thing for tower data. In all cases, both for the airborne and the tower-based data, the accuracy compared to ground truth is in sort of the 10% range, which is also very nice because that's the same kind of criteria that most of the satellite mission concepts have been using for the last 10 or 20 years. Next slide, please. Just a summary of those validation data sets. This has really all been made possible just within the last decade or so, by efforts, by people in the snow community in many different countries around the world. So this is really should be seen as a community contribution. Next slide, please. So in summary, we're working on a 2-frequency algorithm. It's snapshot based, doesn't really require a bunch of. It doesn't use data assimilation, for example. It is physically based. It relies on parameterization to simplify the computations. The background is subtracted out, and there are a number of options for getting the background information. And there's been a substantial validation effort, using both aircraft and tower-based data. A number of papers and theses have documented this. So, and the performance is in the 10% regime. This is really, really encouraging. Next slide, please. And this is all really made possible by a set of advances in remote sensing theory, our understanding of microwave scattering and how radar interacts with the snowpack. That's improved over the last 10 years, as well as the availability of field campaign data for validation I mentioned before. So, and this, of course, again, represents a huge community contribution to advancing us to the point where we think, we have a good algorithm and a good concept for a satellite mission. And I think that's the last slide. Yeah, thank you.
Great timing, Ed. We got a minute or 2 left here. Any questions from the audience? Feel free to unmute yourself and speak up, or if you'd like to throw something in the chat, Ed can monitor that as well and answer offline. I guess, Ed, what's next? That's the question I have.
Continuing the validation and fleshing out rest of the algorithm. The usual work involved in putting together any kind of mission concept.
Awesome.
It's really exciting. I do think, a number of people have remarked that we think the community is in the best position that it's been in like 20 or 25 years at winning a snow-focused satellite mission. So this is really very exciting.
Exciting stuff. Great. Let's move on. Next up is Jeffrey Schmidt. He'll present some work on an analysis of snowpack temperature, density, and cold content across the US West from the repurposed USGS RMS dataset. So, Jeffrey, you want to share your screen? Okay, I can see it great. You're all set.
Right, thanks, Ed. Thanks. Yeah, hi everyone. My name is Jeffrey Schmidt, and I want to tell you a little about my thesis work at CU Boulder Department of Geography. I just graduated with a master's degree and was working with Dr. Mark Serres. And the title of my thesis is an analysis of snowpack temperature, density, and cold content across the Western United States. And here you can see one of those snow sites that Graham Sexton at the USGS has been sampling and running the project. So the background here is just that the climate's changing, and that's influencing the snowpack in the Western United States. And there needs to be a lot more data observing the snowpack to understand what's going on, like validation data sets. So I went ahead and digitized 1,818 snow pits with a group of undergraduate students at the NSIDC, and we created profiles of temperature and density, about 27,000 layers. And this allowed us to calculate profiles of cold content, which is part of what I'm going to talk about today. And then we know that SWE isn't the whole story, that snow temperature is helpful for determining snowmelt timing for water resources. So cold content kind of leads into that. Then just a little about the USGS Rocky Mountain Regional Snow Chemistry Monitoring Study. It's been collecting snow pits for chemistry, atmospheric deposition since 1992, has 180 unique locations. And currently Graham Sexton operates this at the USGS. And I've been collaborating with him to get these paper field forms to digitize the stratified temperature and density. With that data, one of the questions in my thesis I wanted to address is how are cold content vertical profiles shaped by the relative roles of temperature and density? So temperature and density is integrated to calculate cold content. And cold content, as a reminder, this is the equation. It's quite straightforward. There's the heat capacity of ice, and the density of ice, another constant, and then one of the variables is the SWE, the snow water equivalence, depth of water, which is the mass of the snowpack, and then the melt temperature, constant 0 TM, and then minus the snow temperature, which is going to be measured in the snow pit, will result in cold content in joules per meter squared. And all cold content is the amount of energy required to raise the snowpack's temperature up to the melting point. So you can see how that would influence the timing of melt. To understand why cold content is important, just want to go through the snow cover energy balance briefly. There's the net radiation. Well, first off, Keith Jennings in 2018 found that the biggest contributor to cold content is the precipitation itself and the temperature of the precipitation. The second contributor is the radiation, and then the radiation from the sun. And then the third is the atmosphere's interaction with the snowpack. So in the snow cover energy balance equation, we've got the net radiation plus the additions and subtractions plus the sensible heat flux, the latent heat flux, which is also a mass flux, and then the ground heat flux is a little more consistent throughout the year, and then the melt equals this energy storage change per unit time. We're going to get rid of melt because my data set is really just focusing, my work is focusing on the accumulation season, these high elevation sites, and I'm going to assume no melt. So we can say that when this field technician goes out and observes the snow, that this change in energy storage, that's changing, additions and subtractions all through the energy season of every single variable, will result in this change in storage. If you add those all up through time and somebody goes out and measures the snowpack at a particular date, that's going to be the cold content for the season. So it's representing a whole lot of dynamics in this single term. To just show the data set briefly, cold content's on the x-axis and megajoules per meter squared here, and the snow depth is on the x-axis, and the ground snow interface is at 0. And I plotted the mean profile for the entire data set, and then you can see the individual profiles in multiple colors. So what we're seeing on this mean profile kind of aligns with snow science theory. Above about 100 centimeters to the bottom, there's not really a cold content gradient. Let's see, the competing influence of temperature and density, because the density is going down, but the temperature is also going down, tend to create this straight vertical line. But in the bottom 100 centimeters of the snowpack, the cold content is increasing upwards. So there's a stronger gradient, and that as the temperature decreases upwards, the density is increasing upwards. But you can see this large variability in the individual snow pits. Now, to understand the data set, I wanted to just select some stations. So what I did was I took the mean for the whole data set of temperature, the mean temperature of the whole data set, mean profiles, and then now that's what's represented at the 0 line on the x-axis. On the y-axis, we have the depth. So 0 there is the whole data set depth average to get the depth anomaly. So then I took the station means for temperature and the station means for depth and plotted them on the same plot. So we can see in the upper left, we have a deep and low temperature snow pits. On the bottom right, we see the shallow, higher temperature snow pits. And this is kind of interesting that it's showing how the pattern of each location has some consistency and can sort of be classified. But for me in this study, just want to pick some snow pits that well represent the whole data set. And you can see some familiar sites like Big Sky and Togadi Pass. This plot has a lot more information. I take those 9 stations and produce the station mean cold content profile. So cold content's on the x-axis and snow depth is on the y-axis again. But the difference here now is that I've got in the blue lines, those profiles are the station mean profiles for each of those stations. Those gray lines, that's the whole data set mean profile. So you can see how the station mean profile is sometimes different than the whole data set mean profile. Then to quantify the variability for each station against the variability of the whole data set, we have these bars on the left side of each little panel. And the red is the station standard deviation per layer for that station. And then the grays are the whole data set standard deviations. So there's a lot of information here, but just to point out the key for today is that most often the standard deviations for each station are less than the whole data set. But there are some exceptions, and those appear to be the shallower snowpacks like Mount Belmont and 4 Mile Meadow, Wyoming, and Big Sky, Montana, where we can see that the standard deviations per layer at Big Sky are quite a bit higher than the standard deviations of the whole data set. Also note that at Big Sky, the mean profile is like 3 times larger than the whole data set profile. So high variability, sometimes really high cold contents. So thin snowpacks have more cold content, more variability than deep snowpacks. We could really see this at Big Sky, Montana. So a station like Buffalo Pass tends to behave more as we might expect in Colorado, but in Big Sky, it was a little different. So let's look at Big Sky in a little more detail. You can see a picture of Big Sky from the USGS here, the station. And here I've got temp on the left little panel, there's temperature on the x-axis, snow depth on the y-axis, density on the x-axis, snow depth on the y-axis in the middle, and the right cold content on the x-axis, snow depth on the y-axis. So density is kind of behaving as the dataset wide mean does at Big Sky. That isn't always the case across all the stations, but this one, it does. However, the temperature is here, you can see more variable than the whole dataset wide temperature variability. And then the temperature is quite a lot lower than the whole data set. So we have potential for low temperatures, but also potential for high variability where sometimes the temperatures might be high. So how this integrates into the cold content, the pattern is just sort of exaggerated. So the key thing here is, can cold content delay snowmelt or not? So cold content at Big Sky can delay snowmelt or not, depending on the year. Thus, Big Sky might be a good place to measure internal snow temperature. And to wrap up here, the USGS has collected all these data. They continue to do so. The data set's highly valuable, and I'm focused on publishing it at the NSIDC and producing a publication of reference in a data journal, so everyone can get this data and possibly use it for validation. They're sampling about 60 snow pits each year, and I foresee these data having applications in lots of areas of geoscience, but there is a lot of just inherent information in the data set itself, which if you go to my thesis, you can see a much more detailed assessment of how the data set was built, and then a number of other analysis, including some work on time series and trends. So I think this study points to the value of installing thermistors at key snowtell stations to alert planners of when cold content will delay snowmelt timing and when it will not. And that's perhaps, a lot of investment, but even a single, this also shows that even a single snow pit observed at a station that has high variability like Big Sky, maybe a month before peak SWE, could alert planners to see if cold content is playing a role and might delay the snowmelt timing or not. Because there's such high variability, sometimes there probably isn't. And then so that finally the changing snowpack creates a need for more accurate in situ physical snow data. And I think that this project really addresses that concern, and I hope to continue the work. Thank you.
Thank you so much, Jeffrey. We have a few minutes for questions, if anyone has anything. Again, feel free to throw anything in the chat, and Jeffrey can either answer in real time or address it during the next talk. Jeffrey, I wonder, I'll throw a question out at you if there aren't any. I wonder, through your study, did you come across literature about the representativeness of snowtell sites for basins and perhaps vegetation encroachment on some of these sites, and how those implications might play a role in these type of studies?
Yeah, that's interesting. I haven't read about the vegetation encroachment on snowtell, because these stations, I should have mentioned, are oftentimes co-located with snowtell nearby them. But that would be really interesting. I think there's a lot of climate trends and climate variability happening also. But what I like to think is that we got such a large data set here, we're sort of representing everything. And so hence my focus on the variability of what's happening versus trying to pin down absolute values for stations. And I think there's a lot more work to do there, but yeah, that would be another step to continue on this work. And at a site like Big Sky, go check, site visit to understand why it's so variable there. Maybe vegetation is changing. Oof, that could be really fun. What's the groundwater situation? How much moisture is there? I think this Big Sky station is quite interesting.
Awesome. Thank you, Jeffrey. Mike Durand has a has a question in the chat. If you could just look at that and maybe respond in the chat.
Yeah.
And actually,
Okay.
Mike is up next, so he'll see that response after his talk. So before I get to Mike, I just wanted to check, is Andres Zeitz in the meeting? If you could just chime in if you are. Okay, I don't hear anything or see anything in the chat. So up next after Mike will be Angela with the poster presentation, and we might have a little bit extra time between Mike and Angela, so I'll just keep track of that timing. So without further ado, we have Mike Durand and team presenting some work on the retrieval of snow water equivalent from SWISAR measurements in Grand Mesa, Colorado from SnowX 2020. Take it away, Mike.
Thank you. I wanted to start by just apologizing. Some issues emerged with the SWISAR data such that we were forced to kind of pivot and change direction a little bit. But I think this work is something that I haven't presented at Eastern Snow before, and I'm really excited to hear folks' take on it. So the question that I wanted to talk about fits really nicely, really, with what Ed presented earlier, which is this issue related to measuring snow water equivalent from spaceborne synthetic aperture radar at these X to KU bands, and using the backscattered intensity to do that. This technique remains one of the most promising methods to measure global SWE. There's a lot of new approaches, new ideas. And yet this appears that it will remain a piece of the puzzle, likely with the upcoming, the current proposal that's still ongoing for the terrestrial Snowmelt mission by the Canadian Space Agency, ongoing proposal to the NASA Explorer call led by Anna Barros that was kind of woven through Ed's talk. But, and then past mission proposals, which I show a list of here. But the challenge here is that the backscattered intensity that you're trying to use to measure SWE is a function of many things, including snow water equivalent. And in this talk, we're just talking about grain size. Grain size, of course, not the most precise term, but I'll just use that here for the moment. A quick summary of some literature related to this reveals the issue, I think, pretty well. So the Core H2O mission, which was proposed to ESA around 10 years ago, give or take, specified that they needed to have, a priori, they needed to know the equivalent grain size to within plus or minus 15%, which is really stringent. This was repeatedly cited as one issue with the approach. Nick Rudder, several years ago, used measurements from North Slope to show that you needed to have the, if you knew kind of everything else, you needed to have the SSA, the grain size, equivalent grain size of the depth door layer to within even more precise. Then the algorithm that Ed was showing, which originally created by Jiu Zhu, Liang Zhang and others, kind of recast this problem into classification as just needing to know whether the grain size is large versus small, which is more tractable, which kind of gives this hint that requirements for grain size accuracy are algorithm dependent. We spent a little time talking about this in our most recent revision to this review paper on this topic led by Liang, which is in second round of review at Cryosphere and hopefully will be accepted soon. So we had been experimenting several years ago with these random walk algorithms, which are very computationally intensive, but give you a lot of insight into this problem. We wanted to know whether or not a different kind of algorithm might end up leading to a less stringent requirement for grain size accuracy. So a couple quick definitions. Let's say that all the parameters we want to estimate is X. Say that the radar observations, such as the sigma naught, the backscattered intensity, is Y for all the different frequencies and polarizations. And then say we can connect X and Y with the radiative transfer model. Okay, so what a random walk algorithm does is it says we're not going to just give you a single estimate of snow water equivalent from this this measured backscatter. Instead, we're going to have some algorithm starting point, and instead of just iterating and finding a single value of SWE, we're going to let that value kind of walk randomly around the parameter space. So you might feel like a little bit like a snow scientist doing a magnet probe survey as you walk around the parameter space here. I wanted to introduce two more terms, which is the probability of a particular value of snow water equivalent and the other parameters you want to estimate. And then this really important one, the probability of getting a particular radar observation given a particular estimate of the snow values. And I know this sounds a little abstract, so I'm going to try to. I thought I would try to make it a little more concrete by illustrating what actually happens in these. So let's say you have a starting point and of a certain value for snow water equivalent, and then in the first iteration of this algorithm, you'd randomly adjust that. Take a random walk. In this case, decreasing the snow water equivalent. You can take these over to probability space where you've got two different curves, the blue and the green probabilities. And these can be any distribution at all that tell you what the probability of getting the probability is of the pink and the orange places. And if you find that moving to the orange place improves your probability, in this case, it improves it in both the prior, just the the probability of getting a certain SWE, and the probability of getting the observation given that SWE, which embeds the radiative transfer model, the green one, then in that case, you'd accept it. In this case, we're actually moving to lower probability spaces, and so we will reject this walk. And that means that in the second step, we'll be starting from the same place we were in the first one. In the second one, again, in this random example, we move to somewhere where the probability increases in both these blue and green curves. And you just keep going. Here's a third step, candidate, you reject that one. Fourth step, you just keep moving forward. And you do this on the order of 10,000 times. One of the challenges with this approach is that in each of these, in the current setup, we're required to evaluate the radiative transfer model, which starts to get computationally expensive. As an example of what this looks like in actuality, here is the thickness of two different snow layers, the density of those two snow layers, a Markov chain random walk output from our algorithm in both of these cases. And then of course, in each of these, you can get a snow water equivalent on each of these iterations. Then you can imagine taking these algorithms, the MCMC Markov chain Monte Carlo algorithm is sort of guaranteed to give you, if you set up everything correctly, a probability distribution that reflects the actual probability distribution of all of the snow water equivalent given all of the information you gave it, including the observation. So you get a lot more than a single value. So our question is whether or not this approach could be more forgiving in terms of the required grain size precision, which are often evaluated in these more straightforward algorithms where you're just doing a cost function minimization rather than getting the entire probability distribution as your estimate. Some technical details on how we set this up. We're calling this the base R algorithm. It's an adaptation of this paper led by my second author, Janae Pan, former student. And that was done for passive microwave. You can read about that in RSE. But essentially, this is the same process I described in the previous slides. So then for each snow layer, in this case, we're doing a 2-layer retrieval. The algorithm estimates density, grain size, autocorrelation length. So we're using the Memels active model for this in this particular study. The temperature and the layer thickness. We also estimate the soil moisture, the roughness, and the temperature. And we use a snow off measurement to help improve the estimates of these. So we use priors on both the grain size and the snow water equivalent. But for the snow water equivalent, we use this climatology, which we know is kind of biased to reflect, and we do that intentionally just to, since it's a kind of an old model run, but we do it to reflect the fact that many of our models will be biased in the context which we would want to do retrieval. And then we assume that the grain size is basically 1 millimeter plus or minus 1 millimeter. If you convert that autocorrelation length back to an actual physical grain length you'd see with a hand lens. All right, so We evaluate it using the NOSREX tower data. Again, goal was to run on the SWISAR, but with those SWISAR issues that I mentioned, we ended up just having this tower data to compare against. So the typical accumulation is about 200 millimeters SWI. This is a clearing in Tega. And there's weekly snow pits, which is the frequency that we evaluate this algorithm against. So here's some additional example results. This is again for a single snow pit. So this is comparing the radar observations and the snow pit observations on March 23, 2012. So here's the chains, the Markov chains for the correlation length, for the soil moisture, for the layer thicknesses, and for the snow density. One thing I want to draw your attention to is pretty much all of these combinations of density and layer thicknesses all give you a very similar combination of radar backscatter, which again helps highlight how complicated this problem is. So even in these cases, which are very low probability, but in terms of the retrieval PDF, but you still can, by reducing the grain size, end up with the measured backscatter with quite thick snow layers, which highlights the need for the complex algorithms such as this one, as well as the one that Ed presented earlier. Here's a look at sort of all of the data and all of the results. You see the sigma naught values. We're using only the vertical polarizations, VV, for all 4 years. And then you can see, so here are the three frequencies. You can see how well we're matching the snow observations. So here's the snow equivalent accumulation, and the circles are our SWI retrievals. Here are bulk density retrievals. You can see that the bulk density was estimated fairly high in this final year. Here's the sort of SWI scatter plot of the snow pit observations versus the MCMC. So the estimate using that old climatology had an error of about 60 millimeters. We were at about 30 millimeters overall on this. So there's different ways that people have specified what the requirement should be. We had been, at the time we did this work, we were looking at the 20 millimeter requirement from the IGOS objective requirement. So we would really like to see this come down a little bit. Several of the years, in fact, did get closer to that 20 millimeters. If you sort of break up that RMSE by year, you can see that a lot of that error is coming from the final year, which is there was a high density in the actual field data that we didn't capture in the retrieval, and so we ended up underestimating the SWI, even though we were getting the depth about right. A final thing that's an interesting aspect of this problem is this, that the way that this final retrieval PDF looks. So this is what like a heat map of where that Markov chain landed that compares the snow depth and the bulk correlation length. It's just one slice through that retrieved parameter space. What this shows is that for the lower depths, you get higher grain size and vice versa, which is unfortunately the same thing you might expect to see in a spatial location with high SWI in some places, low SWI in others, due to the vapor flux and the fact that the shallower snow would build larger grain sizes. And so this is a interesting complication that comes out of the problem. So in summary, this work just demonstrates the possibility for retrieval with an uncertain grain size, like something like 100%. It's contrast with some of the previous findings that you needed to know this stuff to like 10%, and it kind of agrees with the work shown by Ed earlier. So I'll skip some of the other caveats, just see if folks have any questions.
Thank you so much, Mike. Sorry I didn't get a change in your title if there was one, but I think that was, like you say, a great compliment to Ed's discussion earlier and some of the work that's being done there. Any questions from the audience, either in the chat or if you'd like to speak up, don't be shy. Would love to hear from you. Go ahead, Richard. I see your hand up.
Hi, Mike. Really nice talk. Thank you very much. How important are the priors and getting the priors correct in the process?
So that's the nice thing here, is that with these priors that we chose very highly uncertain priors. We specified that they were, so you not only pick a value for the prior, you also pick its uncertainty. And in both the SWE and the grain size, we chose an uncertainty of 100%, basically. We said we knew maybe the SWE to within, well, maybe 50 or 60%, and then the grain size to like 100%. So I wanted to just illustrate that with one of these slides. So I was spending some time, Richard, with Aaron's recent paper, and saw that you all found a way to get accurate retrievals without using a lot of prior information, at least on grain size, which I thought was really cool.
Right.
So I was trying to think how to like give that a mention as well, and I decided I was unsure, but I've been meaning to talk to you all more about that. Really
sure,
cool.
happy to have that conversation. That's great stuff, Mike. Really good.
So basically what we're showing is that if this is the prior distribution for the grain size, we're able to make that really wide and not require that super precise grain size.
Nice.
Awesome. I guess I'll just throw out one more opportunity. Is Andres Zeitz in the meeting? If so, please speak up.
Hi, yeah, sorry for being late, but I'm here now.
Awesome, great. Well, yeah, I know there was some confusion on the poster presentations, and there was just an email from the Joint Congress about them changing up their format for some of the poster session only. So look for your emails. It looks like there's a Gather Town where folks can sort of enter and look at and engage with posters a different way. So look at your emails from that. But Andres, would you like to try sharing your screen and talk through your posters? You have 10 minutes to do so if you're available.
Sure. Let's see. You might have to, I have to change some system preferences, so it might be best if I
go second, maybe?
The lineup.
Yeah, that's fine. Angela, are you available to jump in?
Yeah.
Great. Why don't you go ahead and take your 10 minutes and then we'll check in with Andres afterwards. So welcome to Angela Rienzo. She'll be discussing her poster, which is evaluating passive microwave snowmelt detection methods with ground snow observations. Thank you.
I just want to, oh, sorry, I just want to clarify, is it 5 or 10 minutes?
I think, yeah, before going to that, we are total of 10 minutes for the poster.
Oh, sorry.
So, yeah, it might be, it's just 3 or 4 minutes, it would be enough to.
Okay, great. 3 or 4 minutes. Sorry, Angela, appreciate it.
And can everyone see my poster?
Yes.
Okay. My research is on evaluating passive microwave snowmelt detection methods with ground snow observations. So the purpose of my study was to determine if satellites can be used to detect snowmelt in place of ground observations such as SWE and snow depth, since satellites can be used more as a global option versus snow stations that are more scattered and more expensive to build. So the main research questions that I went in looking at are, is the satellite data detecting the same type of melt event that SWE and snow depth are? And is this method more accurate in certain types of snow climates or certain regions? So the data I used, I started with daily SWE and snow depth data from around 600 snowtail stations. I then extracted whether or not melt events had occurred each day based on whether the SWE and snow depth were decreasing or increasing. I also used AM3 satellite data for the satellite melt events, and that was derived using brightness temperature using the new method from Tuttle and Jacobs 2019. I also downloaded snow classes for each of the stations from snow classes determined by Sturm and Liston in 2021. And to calculate the agreement, I used 2 different types of agreement analyses. First, I did a one-to-one agreement to look at the fraction of days when both the satellite and the ground observations saw melt. And then I also did a normalized seasonal agreement, which just looked at comparing the overall timing of the melt events throughout the year. You can see in these figures some examples of SWE on the left and Snowdep on the right, and the matchup with the satellite. And both of these, satellite is blue and the red are the ground observations. And you can see there are very big variations and also variations in the size of the data sets as well and the number of melt events they see, which is why we want to normalize that as well. So for some of our results, we ended up with about 6 total agreement data sets for all of our patients. For this first 4 is for our one-to-one agreement analysis, and we did not end up finding any significant results between the different snow classes. And the agreement ranged from between 0.3 and 0.5 fraction out of 1. Then for the normalized seasonal agreement, we were able to find that the maritime snow class, which is the red one in the center, was significantly higher in agreement over most of the other snow classes for the snow depth. Also found in this figure up here, there was a regional higher agreement in some areas, such as down here in the Sierra Nevadas, much darker blue points compared to the rest, and some other areas in the mountains, the Rocky Mountains up here as well. So what we concluded in the end was, because a lot of the agreements were not much higher than about 0.5 out of 1, that the satellite is not in fact always seeing the same type of melt events as the ground data, because there are many more factors at play with both SWE and snow depth. So we won't see an exact one-to-one agreement. But we do believe that the satellite might be more useful for detecting melt events in the midwinter versus the spring seasonal melt, which is where the agreement seems to be the worst, as you can see back in both of these figures here. This is around the springtime, where the SWE and snow are much higher. So in the future, what we plan to do is remove the melt events in the spring to see if there's a higher agreement just in the midwinter between the snow depth and the satellite.
Thank you so much, Angela. We're running a little late, so I'll ask if anyone has any questions, please throw them up in the chat. I've got some questions. It looks great work, Angela. I'm familiar with most of it, but I see some new results there. So I'm going to throw some questions in there for you. But it looks like you have one there, Angela, if you could address it. And if you could stop sharing your screen, and we'll ask Andres to try sharing his screen now.
Sure. I think it's working now. Here we go. Please let me know if you don't see my poster.
Yeah, it's coming up. Yeah, and you have your cursor. I can't see your cursor. Now I can. Yep. Great. Go ahead. You have 3 to 5 minutes here.
Wonderful. So hello, everybody. Good morning. My name is Andres Sates, and I'm currently a PhD student at McMaster University, although the work I'm presenting is something I've been doing in the intervening years since I started. We all know that snow is a primary component of hydrologic cycle across Western North America, primarily where it's mountainous. And snow water equivalent is the key variable that a lot of us are interested in. And there have been a lot of efforts to develop empirical models that can relate snow depth to snowpack bulk density, because snow depth is much easier to measure in comparison to bulk density or SWE. And so considering a lot of the previous modeling efforts, they tried to make the best estimates of bulk density by fitting these empirical models to specific regions, or having them fit to certain months or elevation bands or snow classifications, and that works fine, but the resulting models aren't strictly broadly generalized or like broadly applicable. And that's what I wanted to try and work on for this study with this research. So my idea was to explore how cumulative degree days and climatological predictor variables could be added to these existing models to make them more broadly applicable and retain some good model performance as well. So working on this idea, I fit a nonlinear model that was first proposed by Matthew Sturm in 2010, which you see in the center here. This is the general form of it anyway. And then I derived the additional predictor variables, the degree days, using gridded reanalysis data from North American regional reanalysis, and the climatological variables extracted from Climate NA. Fit a good model. Cumulative positive degree days index was a good predictor. It was significant and produced good results, as you can see on the figure here. And then comparing it to another recent study reported in literature, a key improvement is that there is minimal seasonal bias. You can see the residual errors through time, through the accumulation and ablation season are quite consistent, around 0, whereas other studies have, and this study has a little bit of bias as well in terms of its prediction errors, but generally that's a key improvement that we found. There's of course still work to do because there's some spatial bias as well. I'm happy to talk about this later, and I'll take any questions that folks have.
Thank you so much, Andres. We are running a little late on time, so again, I will ask folks to add their questions into the chat for Andres, and there's some good discussion there already from Angela's poster and others, so feel free to jump in there and take a look at those. But thank you, Andres. We'll move on to the next presentation, and that is Annika Forget. I hope I'm saying that correctly, Annika. Her presentation is using machine learning to estimate snow cover from ground surface temperature measurements.
Oh.
We can see your screen, okay?
Okay, perfect. And you can hear me?
We can, thank you.
Okay. So hi everyone, thank you for joining me today. My name is Annika Forget, and I'm a student at the Northern Environmental Geoscience Laboratory at Queen's University. And today I'll be discussing some of my master's research, which focuses on determining snow cover from ground surface temperature measurements. So as many of you guys are probably aware, snow cover is a critical ecosystem variable, and it greatly impacts the ground thermal regime, especially in Arctic and subarctic regions. However, because of factors like topography, wind, and vegetation height, snow cover varies hugely over short distances. So we would often need many snow cover measurements to understand variability within an area. So one way researchers have tried to address this issue is to use large deployment of low-cost ground surface temperature loggers across the area of interest, and then to build some sort of method to extract snow information from these loggers. Usually methods for estimating snow cover from data loggers use daily temperature fluctuations in the ground, or differences between temperatures in the air and the ground, with some type of local threshold determined either visually or based on previous literature. So these methods, though widely used, have rarely been tested across multiple study areas or even across different conditions within a local field site, and also rarely consider differences in ecosystem and snow characteristics. So my research aims to address some of these concerns of these more common methods by developing a new approach for deriving snow cover information from ground surface temperature data which is based on a machine learning algorithm that is trained on soil temperature and snow simulations from the Northern Ecosystem Soil Temperature Model, or NEST. So this model was calibrated to our field research site at Pinware River Hills, or PRH, which is at the southern end of the discontinuous permafrost zone in Labrador, where we have also been conducting modeling and field investigations of both snow and ground temperature conditions since 2019. So in this talk, I will be comparing model results produced using this new machine learning approach to those derived from two more common methods to show differences in the model's snow cover duration at PRH. So just as a quick refresher, in this study, we use random forest as our machine learning algorithm, and this builds on the theory of decision trees. So hundreds of decision trees are built and assessed with a variety of different combinations. And these are combinations of the input variables. And these input variables, there's the different combinations. So they're rearranged to obtain the lowest prediction errors. Researchers typically train their random forest model on a series of variables that are considered to be meaningful for prediction, using about 70% of the available data for training, while 30% is usually used for model evaluation. So if performance is deemed by the researcher to be suitable, then this trained model can be used to predict for new data. If all the required explanatory variables are available, then these, again, can be applied. Random forest is less affected by multicollinearity and outlier data than other approaches, but does depend on the training data to be representative and covering the range of conditions meant to be simulated. So specifically for my model, we use 15 explanatory variables, which can be easily calculated from air and soil temperature loggers in the field to predict the probability of a given location being snow covered based on these variables. So for comparison, my first method that I use is the daily standard deviation of ground surface temperature data. So this is often used since the daily fluctuation in ground surface temperature decreases when there is snow cover due to the insulation from the fluctuating air temperatures. Based on literature, the minimum standard deviation used is usually between 0.2 and 0.4. And for our purposes, we obtain the ideal threshold for our field site from the NEST simulations to compare the best possible outcome to our random forest model. The second method used to compare builds on this by including the daily standard deviation of air temperature as well. So we use the optimal difference between the daily standard deviation of air temperature and the daily standard deviation of ground surface temperature. So this value varies depending on location due to differences in mean air temperature, but it's typically between 0.8 and 1.2. So again, these optimal thresholds were achieved mostly by trial and error to locate the value with the lowest error from a confusion matrix of snow cover or not based on the NEST simulations to again make sure we're comparing the random forest method to the best possible choices made from the other methods. So here is a more visual representation of the model analysis that were performed. So a total of 6 different model simulations of ground thermal and snow conditions from NEST were obtained from 1981 to 2020 using ERA5 climate data and the soil profile that was previously calibrated for our field site of Pinware River Hills. So each of these simulations considered different combinations of snow accumulation and vegetation characteristics, providing a huge range of local conditions to test against. So the training data set was used to train the random forest model and also develop the optimal threshold for the 2 more common methods. And these data sets were kept the same and then were evaluated against the test data for the accuracy assessment. And then comparison between the techniques were done. So because there's no guideline on deciding on the right thresholds for the simple approaches, I just want to again highlight that we used the optimal threshold for the two common methods, and this was done through trial and error. So jumping into results, we'll begin by discussing our implementation of random forest. So these are a lot of points, but this is the 40 years of daily snow cover probabilities shown by hydrological date, which begins on October 1st and ends on September 30th. So because there's 40 years of data here, we can see variability reflecting the anomalous conditions that occur from time to time. But generally, we see that winter months have the highest probability of being snow covered. Some are the lowest, and shoulder seasons have the largest variabilities. Also with random forest, we can also explore the different how different variables influence our results with the variable importance plot. So here it is, and how it works is it shows the increase in mean squared error that occurs when that variable is excluded. So higher errors for a specific variable can be interpreted to mean that this variable was more important. So for my random forest model, here are the 15 different explanatory variables, with the most important being the daily maximum ground surface temperature and the least important being daily maximum air temperature. So theoretically, this makes sense because we know that air temperature can still be quite high even on days where the ground is still snow covered, whereas warm soil temperatures usually do not allow snow to persist very long. So looking at the different variables, we can also see that using a single measure, like some of the common methods use, may not sufficiently represent snow cover conditions. So for the method comparisons, we can show this over the next couple slides that I have. So here we can see comparison between the predicted annual total snow cover days and the model simulated total snow cover days for the three methods we tested over those 40 years. These are the out of sample comparisons. So what was used on the test data set, not the training data set. And also just a note for the random forest model, we used snow cover probability of 0.5 as our cutoff. And just to be able to compare between the two common methods, which again are based on the optimal threshold you could possibly choose. So what we see here is the out of sample results that random forest seems to be the less biased predictor, though the standard deviation method does generally outperform the air surface difference method. So using all simulations across all years, we can see that the trained random forest model produces lower medium annual error in snow cover for both the within and out of sample comparisons, even though the improvement is less stark in the out of sample data set. Generally, random forests kept annual errors below 10 days per year, whereas the other two techniques regularly were above that threshold. So now quickly just stratifying our results by simulated ecotypes, you can see that random forest once again produces lower median error than the two comparison methods, but we do see some evidence that its performance in wetland simulations may only produce comparable errors to those methods. As such, it might be worth considering further development of a separate model for extremely wet environments. So my next step with this research is to use our trained model to test their performance on field measurements. So we have field measurements collected at Pinware River Hills, where we have co-located ground temperature and snow information for the past several years. We also plan to test our model for other locations in Labrador and have already done so for another field site in Northern Labrador, where our results look very promising, indicating possible transferability of our model to other regions. So we hope that further deployment of this approach will give us a new method to analyze the thousands of ground surface temperature loggers that have been deployed across the Northern Hemisphere, with the goal being to have methods of getting accurate snow cover information that are comparable between regions. So I just want to end by saying thank you all for listening, and I would like to take the time to also thank all these partners for which this work would not be possible without. It would be a pleasure to answer any questions you may have. Thanks.
Thank you so much, Annika. You've gotten us back on schedule. That deserves a few questions from the audience, if there are any. Annika, I guess I'll throw a question out there. Are there other machine learning techniques that you would like to explore, or what's the benefit of random forest versus some of the other machine learning techniques that are available?
It could be a possibility to explore other techniques. It's just random forest, it gives you a lot of insight into the variables you include. So it can give you a bit more information. It's also pretty simple to run compared to other methods. So just computational time, especially if we want to apply it to a bunch of different regions, it might be more useful.
Excellent, sounds great. So
Thanks.
please do follow up with Annika in the chat if you have any further questions. But at this point, we'll move on to our next presentation, which is Ryan Webb, and he'll be discussing characterizing the role of snow for liquid water storage and transmission, a ground-based remote sensing and modeling sensitivity analysis. Go ahead and share your screen, Ryan, when you're available.
All right, can you see that okay?
Yeah, looks great, thank you.
Okay. All right. Well, hi everybody, and thanks for being here. I'm just going to talk a little bit today about characterizing the role of snow for liquid water storage and transmission. So how that liquid water gets kind of transmitted around a landscape. And we used ground-based remote sensing techniques as well as modeling sensitivity analysis. I'd like to first recognize my co-authors here. This was in collaboration with folks over at Instar and at CU Boulder, Keith Musselman, Kate Hale, Sivan Ciafone, and Noah Moloch. And the funding was through the NSF. So the overall goals of this project was really to assess the mechanisms that control that distribution of liquid water during the snowmelt season in an alpine environment. Our specific research questions was how does that liquid water storage change throughout the melt season, and how accurately can current hydrologic models simulate what we observe in the field. The site that we used for this study was the Saddle Catchment. It's just under a ½ square kilometer here. Let's see if I can pull up the laser pointer. So back in the left panel in the background there, that's the Continental Divide. And so all the wind does come pretty much right down this ridge line, westerly winds. And so the ridge line for the watershed delineation is kind of like right along here, kind of goes up in this direction and then comes down here. So we can see this is a west facing slope. Even in the middle of winter, does not accumulate much snow, a lot of scour and a lot of deposition on this leeward side. The building here, you kind of zoom in, and just for a sense of scale, the drone pilot for these pictures is right there. You can kind of get a better sense of the hill slopes here. So I kind of think of it like a staircase. So you kind of come up this hill, you hit like a staircase landing. It's pretty flat right here. And then you make like a 90-degree turn and you go up the rest of the staircase. So it's like an east facing slope here, a flat area, and then down on a south facing slope. And that's kind of the main survey area of those two hill slopes and the flat area in between. And our survey techniques, we used a combination of LiDAR and ground penetrating radar. So the GPR that we were using were 800 megahertz as well as 1600 megahertz. We predominantly used 800 megahertz due to just some of the signal was lost at the higher frequencies for liquid water contents. But in general, this size of watershed and these conditions, the LiDAR was a little more difficult, a little more time consuming for the surveys. So we conducted LiDAR scans about 3 times throughout the melt season, and GPR surveys a lot more frequently. Those only took about an hour to cover the entire watershed area. And we used the depth constrained by LiDAR and the time of the radar through to estimate the dielectric permittivities, which we could back out the liquid water content. For the purposes of time, I'm not going to go into too many details on that here, but I'm happy to have a conversation about those methods offline if anyone would like. From a modeling analysis, we used SUMA, the structure for unifying multiple modeling alternatives. And today I'm just going to really be talking about the sensitivity to water storage and flux parameterization, so hydraulic conductivity, as well as other storage components using like the Brooks and Corey equation. Here's just a general structure for hydrologic models. So we generally have a snowpack with however many layers the model allows, and then some kind of melt that goes into storage. And once that storage is overcome, it's released from the snowpack. And what I'd like to focus on here is that separation of the snow and soil. So once the water is released from the snowpack, any hydrologic model generally treats it more like rainfall. So it's no longer thought of as specific to the snow. It more just, if you have runoff across the surface, the snow is magically, floating above the ground surface, and it's surface runoff without any attenuation through the snowpack. So that's kind of the general hydrologic structure, model structure that we see get used. So going into some of the observation results, here I'm showing 3 panels. On the left, it's the early melt in May 23rd, sort of that moderate melt in the middle of June, and then peak melt at the end of June, June 27th. These little insets here are actually showing the hydrograph of the stream at the outlet. So that black line is the stream flow, and that red line is showing the timing along that hydrograph for each of these panels. The brownish colors are the LiDAR derived snow depths, so that the darker colors here are shallow snow depth, and then white is either no snow or just sort of where the LiDAR did not see. And these lighter colors are for the deep snow. And this snowdrift down here was about 7 meters deep at peak, mid-May, right around this survey time. But just for visualization, I capped it off at 5 meters. And then the GPR surveys along these blue tracks, where we derived the liquid water content. The lighter blue color is low liquid water, and the darker is going to be higher liquid water contents. And we can kind of see, early on in the season, some liquid water starts to accumulate and being stored in the snowpack in this flat area. So the hill slope kind of comes up here, get flat area, and then that eastern hill slope is right here. And this area kind of stores that liquid water throughout the entire melt season. As the season progresses, you kind of get more areas of that high liquid water, but areas similar to soil moisture, areas that have high liquid water content storage tend to remain that way throughout the season. And the distribution of that in a histogram looks kind of like this. So the beginning of the season, the melt season, May 23rd in blue, June 27th in red, you just see that shift into kind of higher liquid water contents, as you'd expect as the snow continues to melt. But we did see a good percentage of liquid water above 20%, which was a little unexpected. But it's just showing some of the high liquid water that we see at our site. Oh, and one more thing. So we did do some regression analyses. Again, for time, I didn't want to get into it too much, but in the paper, the results are there. And we did see shallow snow tending to have higher liquid water content. Some of the modeling results, right? So if we look at this flat aspect, so right at more or less the base of this east-facing hill slope, that was a site that we looked at. The east-facing hill slope, right in the middle of the hill slope, where you would tend to choose to dig a snow pit, and then the south aspect, right in the middle of that snow drift that forms there each year. We chose a spot that was about 6 meters deep, not quite the deepest location of the drift, but still pretty deep. And what that looks like for snow depth and SWE, these gray bands are the entire range of all simulations. And then these point and whiskers are all of our field observations within a 20 meter by 20 meter box around that point location of the simulations, to kind of show the variability of not only the models, but of our observations in that area. And we can see that the models did pretty good for depth and SWE, as we would expect, right? So for decades, these have been the go-tos for calibrating models. the main goals are generally snow depth and SWE. So it's no surprise that we're getting pretty good results here. But when we start to look at the liquid water content, that flat aspect area, the observations were well outside the range of simulations. And just these added colored lines, the blue line is that slow draining, so slower hydraulic conductivity. Black line is sort of that moderate, and this red is a really high hydraulic conductivity, so fast draining, it doesn't hold on to the water as nearly as well. So that east aspect, the simulations were pretty good for the slower draining parameterizations. And then that south aspect near the drift, about half of the observations were outside of the simulation range. And then half of them were within that range. But overall, most model parameterizations underestimated the liquid water content in the storage. So, this east aspect shows promise. This also tends to be, where we would dig a snow pit that's more representative of a hill slope. And then this flat aspect is, kind of where we would not tend to dig a snow pit because it's near the base of that hill slope. And we know that some of these factors come into play. So I think it's just goes to show how variable these conditions can really be, especially with liquid water content. And some of the processes that we see as occurring and causing some of these issues, they're not included in a lot of models, are things like this. So if we think of this as the hill slope, we have this lower hill slope, that flat area, and then the other hill slope. And if we get these wind drifts, right, you can get some ponding on those ice lenses. And some of the snowpack models will include that with some preferential flow around those, but a lot of hydrologic models might not include that. But the rest of these processes, like, if the groundwater table actually rises up into the snowpack and you get this capillary rise, this increased liquid water storage in the snowpack, there's not currently a model that I know of that actually includes that. So I think that's a big part of what's going on with our observations compared to our models. These diversions across different layer interfaces. So again, models don't tend to have these lateral fluxes across the snowpack. So a pixel will have, a snow component, but the lateral flow doesn't occur until the water is released and goes into the soil or something. Similar to that, if you have, this lateral wetting front moving towards the stream, it might go faster in the snowpack relative to the lower conductivity soils, depending on, interflow, preferential flow paths, things like that. And then also, if you have this convergence of flow paths along ice lenses and things, you might have infiltration excess. So basically water coming to that soil surface a lot faster than the soil can take in. And again, that's just sort of that lateral flux in the snowpack that doesn't get represented in a lot of models. So going back to this traditional hydrologic model structure that we tend to see, we're kind of proposing these improvements for snow-dominated watersheds. So really coupling that snow and soil to allow this porous media flow through. So if there's surface runoff where there's a snowpack, instead of treating it like rainfall runoff, thinking of it as porous media flow, really going through the snow, resistance, like kind of like a gravel or something, increasing this liquid water storage. So if we do have that groundwater table coming up above the soil surface, allowing that increased storage, and then those just other lateral fluxes across ice lenses or things that, have been shown with some finite element modeling. I know Nicholas LaRue has done some of that. I've done some of that at the plot scale, smaller scales, but I think scaling it up to the small watershed could be beneficial. So just to kind of wrap things up, these patterns that we're seeing at this small watershed scale are very similar to what we saw at the plot scale in this same watershed. So things tend to scale up relatively well. And these parameterization schemes that are commonly used in snow models tended to underestimate liquid water content in all the cases we looked at. So there was some that were pretty close, but it was still tended to be underestimating liquid water content. And if we improve the parameterizations, that could be beneficial for hydrologic modeling, thinking about the connectivity to the stream, or for feasibility of snow remote sensing, getting that liquid water content correct for these sensors that might be a little more sensitive to liquid water, and really trying to think of how that will benefit future missions. Of course, the remaining questions are like, how does this aggregate up for, if the sensor's, multiple kilometer pixels, that might not be as important, but we don't know. So just to want to acknowledge the rest of the team and the NSF funding. And if you're interested in this work, this paper is published, but I'm also happy to answer any questions now or via email. Feel free to reach out to me. Thanks.
Thanks so much, Ryan. We do have time for one question if there's anything out there. Vincent, go ahead. I see your hand up.
Hi, Ryan. Thanks for the very interesting presentation. I like the conceptual model. Like one of the challenges certainly for modeling will be the scale. And you mentioned this, like the modeling that you have done previously at the plot scale. Could you comment on the transition when you will want to deploy this approach at the, let's say, the scale of small catchment? And what is subgrid and what needs to be resolved? Could you comment on that?
Yeah, I can comment on that. That's so I think that is still somewhat of a standing question. I think that some of the work I've done in this area in Colorado shows that everything will kind of aggregate at like the 10 meter by 10 meter pixel scale. And if you go lower than that, then just the natural variability in depth kind of creates those layers, ice lenses and things that might cause more lateral fluxes across pixels. So at least in this area, if you when you start scaling up, if you go maybe to 30 meters, it might not matter as much, but I think I want to investigate that a little more, just to see where that water really is coming from at the base of that hill slope. If there's a lot of lateral fluxes to the snow, or if it's mostly sort of at that soil interface, as well as that subsurface interflow flow paths coming and converging with those. So trying to figure out those. I think there's still some work to do to determine that, but good question.
Thanks, Ryan. It looks like there's another question in there in the chat for you, if you could address that. And thanks to Annika and others who are monitoring the chat and answering those questions. In the sake of time, we'll move on to our last presentation, which is by Richard Kelly. It's entitled The Airborne Cryosphere Observing SAR System, CryoSAR. First observations of terrestrial snow and lake ice during winter, or alternatively, a snow, soil, sea ice, and lake ice observing system.
Hey, thanks very much. Can you hear me all right, Eli?
Yes, I hear you great.
Excellent. Okay, thanks very much. Thanks to the organizers of the session. It's been really interesting to hear the different talks today. So the title of the talk is a little bit different, and I'll get to that in a minute. But I wanted to talk to the project we've been working on for some time now, the Airborne Cryospheric or Cryosphere Observing Synthetic Aperture Radar System, or CryoSAR as we're calling it, which is a snow, soil, sea ice, and lake ice observing system. A quick acknowledgement of my co-authors and collaborators. Is actually more than this, but for this particular part of the work, we're working with, well, my postdoc, Aaron Thompson, has been doing a lot of the heavy lifting here. We're working closely with Adriana Meta from Meta Sensing, Jim Hodgson at Lake Central Air Services on the integration side. And then we've got some people on the ground, Alex Langlois, Alex Roy, Laura Brown, Aaron Burrow from different universities, and Chris Dirksen at Environment Climate Change Canada. So this is a kind of this is a group effort, really. So this project goes back a little bit. Patience is a virtue, I put here, because we've been working on this since 2017 when we put a proposal in for an airborne system. We've been doing quite a bit of work with ground-based radar remote sensing at KU and X-band for some time now. You may have seen some of the work we've done, but there was an opportunity to acquire an airborne system, and that's what we did. And be careful what you wish for, because once you get one, you have to start working on it. And it was funded through the CFI. Project goal was to acquire a KU and L-band system. And the idea was to have something that's fully polarimetric and capable of what I call an agile deployment for cryospheric science and other surface applications. And I'm just going to move this thing out of the way. Sorry about that. The idea was to specifically target science questions around snow accumulation, sea and/or lake ice, glaciers, ice sheets potentially, and then soil moisture and other land surface properties. So the system build was metasensing. We manufactured the SNOSAR instrument, and the target platform for this is a Cessna 208, 208B Caravan or Grand Caravan, which is, according to, I think this is on their website, a utility aircraft used for training, commuter airlines, VIP transport, air cargo, and humanitarian missions. And I'll add to that, skydiving clubs use it, which is actually why we're really interested and why it works quite well for us. So the key thing, one of the key things about this instrument package is that it is we think of it as a community instrument. So we're working collaboratively with as many people as who are interested. And much of the work we're doing at the moment is in support of the TSMM, but there are other projects that we're working on as well. And to support, and we're always open to colleagues across the snow community, but the wider cryospheric community as well. And you can see some pictures of at the bottom here, just what the system in it, the system platform looks like. There's for those who don't know, this is a Cessna 208. You can see the door in the middle photo has is actually the jump door for a skydiving club where this aircraft is sourced. Okay, so the actual CRYSAR instrument then, what I'm going to do is I'm going to just step you through the instrument, and then I'll talk about the deployment and the change of plans that we had to have for this presentation. So the system is a KU and L-band system, 13.5 and 1.3 gigahertz. And you don't need to read all of this in the interest of time, but there's a few things that's worth pointing out. The L-band is a pulse system, and which kind of means you get a slightly cleaner, potentially a slightly cleaner construction of the image from the acquisitions. The FMCW system is on the KU side. I'll note that the system on the KU, it can be interferometric. We can actually do single pass interferometry with this. That's a bit further down the line because we're still learning how to use it. The antenna polarization properties, we have fully polarimetric systems, so we can transmit and acquire in all modes, so dual but all polarimetric states, so HHVV and then cross-pol states as well. And the nice thing is it's fairly lightweight. That's why we kind of like it on something. We wanted to find something that would be quite deployable. In aviation terms, agile is not something that you want to really use too much, but I would say this is on the more towards the agile end of deployment, because when you put it onto a 2.8, this is what it looks like. So the left-hand side has got the RF units tied down to the floor. The middle photograph, you can see the antennas are mounted on a door mount system that we've got now. And once you've got your data, we're able to process it, and we're doing a lot of SAR processing and a lot of learning of SAR processing at the moment. There's a processor on the right-hand side. It's a very noisy workstation, but it seems to be doing the job pretty well. So when you install it, then typically from the manufacturer's perspective, the photograph on the left side is a pretty dynamic installation of the system. This is actually from a campaign that Metasensing have been helping out with. But you can see the roll door at the top. That's typically for a skydiving club. That's where they roll the door up and then they jump out of the aircraft for the skydiving. What we actually were able to do was to procure our own doors. I think this is something that's been done by Environment Canada before as well. But we now have our own doors, so you actually have the aperture is closed in a closed configuration. And you can see the antennas in that middle photograph mounted through the windows of the system. And the nice thing is we can access the equipment on the ground quite easily just by opening the door. So Lake Central have been absolutely instrumental for us in this this installation activity that we've been working on. Okay, so originally the talk was going to be all about what we were doing this last winter, but unfortunately we didn't get to where we wanted to get to. But the project is a project that's funded by the CSA, and it's a project to look at snow cover, snow accumulation in Ontario and Alberta over a 3-year period. And these are the 3 different objectives. Firstly, to acquire L and KU band data from the CRISR in the winter of 2022 and the fall of winter 2023. And then at the same time, objective 2, to conduct field campaigns on the ground to collect snowpack measurements so that we can test retrievals, which then feeds into objective 3, which is to support the terrestrial snow mapping mission that is in planning and in preparation and development at Environment Climate Change Canada and the Canadian Space Agency. So this is a 3-year project. So the first 2 years acquire data, and then the 3rd year would be to work and test on retrieval capabilities of using the data, so you can perhaps simulate the actual TSN effort. So the field sites that we identified for winter 2022, one is in a place called Halliburton. You can see the pin just to the right of Huntsville on the map, and the other site was up towards North Bay, which is the Powassan field site, and that would be a more land-based site that we were due to explore. So the Halliburton field site is a bit more lake-focused. So here you go. This is what it looks like. This is a site that Laura Brown from the University of Toronto has been working on for some time, and has a nice array of instruments for lake ice studies. Also, there's some snow on some terrestrial, some land-based snow studies they do as well. It's highly forested, so the focus then really is on the lakes. And the goal was to fly this area during the 2022 winter, sort of January, February timeframe. The other site is a really nice site up near North Bay at a farm field site at a place called Powassan. And it is fairly open. The farmer doesn't. It's not it's animal farming, I would say, is the dominant thing here. So it's mostly pasture. Doesn't get plowed too much, although they did plow this last winter. You can see some small forest stands. So it's a very manageable site. The width of that grid is probably about 200 meters, something like that. So it's really nicely accessible. So in thinking that we would be able to fly the aircraft, we actually had a really nice small field campaign in the first week of March, where we had people on the ground measuring snow microstructure using several different tools like IRIS. We got a new little infrasnow device that is a smaller version of an IRIS to play with, and that was fun. We had groups from Sherbrooke, from Waterloo, and Trois-Rivières from the 2 Alex's group and our group. We had a KA snow radar that we were able to deploy. We had usual Magna probes as a permittivity probe, and we could do structure from motion. I would say one of the highlights for this winter has actually been able to get out into the field post-pandemic, or as the pandemic has come to an end. And it was really great to see 12 people out in the field, many students, many of whom have not actually been into the field, perhaps during their graduate master's degree or PhD yet. So it was a wonderful experience. So great training, really nice for us researchers to get back out into the field and do some work. And here you go, just to give you a sort of a feel for some of the things that were going on. This is just shaving off layers of snow so that we could take the KA, the ground-based KA radar system, and look to see what the profiles the snow profiles look like as you kind of excavated snow from the surface. So patience is a virtue. We waited a long time to get the equipment mounted. It was almost mounted. We had approvals to transmit and receive from the relevant appropriate authorities, but the final Transport Canada application remained pending for this time. So unfortunately, we were not able to fly at the same time. So we had to do a bit of reconfiguration. And so unfortunately, that's why the title of the talk has changed a bit. And really, this is kind of it's showing what we are able to do probably next winter. And for the next Eastern Snow Conference, I'm hoping that we'll be able to show a lot more snow-related work. However, patience is a virtue. Things don't always go to plan, but we were able to fly. And on the 14th of April and 22nd of April, we flew the two sites, one over the site at Halliburton, which is the lower, you can actually, there's a photograph from the aircraft. And on the right-hand side is the Powassan, the northern site, the farm field site. Clearly there's no snow there, but when you look at this from a radar perspective, here's a Google Earth photograph. And here then is here's our first uncalibrated first look of an L-band acquisition over the same domain. And you can see we're picking up the lakes, and we are learning a lot about radar processing, and the meta sensing are very keen to explain that there's a lot of post-processing and a lot of uncertainty that can be squeezed out as you gain your skill in the post-processing. However, you should be able to see that there are lakes in the field of view that are pretty clearly evident. And the question now is do some calibration work on these data. So for the northern site, also we flew the region, and this is the Powassan site, and the field site is where the pin is, and it's you're seeing this is a KU band now, so this is cross pole. So you can see features in the site. You can actually see, if you see my mouse, but up here, this is actually the farm field site. This is a plowed field over this area here, and so there's work to be done with this. But again, we're excited. It's like giving birth to a child that's you've been in labor with for about the last 5 years. So this is exciting stuff for us. So the current status: every day is a school day. We're learning, and certification for the instrument is almost complete. We'll be able to deploy it pretty much wherever there's a Cessna 208 in Canada or in the US, or anywhere probably anywhere across the planet. We've got plans for a bigger field campaign to do the snow work next winter. We've got some summer plans for 2024 in the Arctic that we're trying to work on, and then summer 2022 this year we have potential deployments for the SmartVex experiment. And it is a community instrument, and I think the two things here is a community instrument. I think the other thing is it's really great that with all the work that's been gone on and through this session, some of the radar work that people are engaged in, there is definitely a capacity building that I think is happening in this radar field that we're really happy and excited to be part of as well. So I know I went a couple of minutes long there, but thanks very much for listening.
No, that was excellent, Richard. Thank you very much. There are a few questions in the chat. There's a quick one just about how did the infrasnow sensor compare to the IRIS, if maybe you could address.
Yeah, it's interesting that we learned quite a bit. It's all about trying to. I think if you place the infrasnow instrument straight down on a snow, that on the snow layer, that is the best operational way of using it we found. We haven't done the analysis yet, so I can't tell you how well it matches up. But that is, we did have the IRIS and the infrasnow together for several sites, so we will be doing that analysis, and perhaps I'll be able to report on that next time round.
Thank you, Richard. There are a few radar-specific questions that we probably don't have enough time to address, but feel free to take a look at them. I'd suggest those who posed them in the chat, if you'd like to reach out to Richard directly, I'm sure he'd be open to answering those questions.
Yep.
But first of all, I want to thank all of our presenters today. Thank you so much for participating in our snow session and this joint Congress of the ESC, CGU, and CMOS. It was a great chance to see folks again and to hear about the exciting work that everyone's doing. I'll plug our other two oral sessions, part 2 and part 3 of the novel approaches in seasonal snowfield measurements. That'll be 12:55 local time, Mountain Time, and 2:55 Mountain Time for parts 2 and parts 3. My colleagues I'd like to, my co-conveners, I'd like to thank as well. They'll be hosting those sessions, in Sing Chow, Melissa Reason, and I'm not sure if Carrie Vujicic is participating, but she did help us in setting up the sessions. And again, the changes to the poster discussion sessions, please refer to that email from the Joint Congress. There will be, you'll be able to navigate through the Congress portal to GatherTown, where will be an online meeting, poster session, discussion session meeting, where you'll be able to interact with folks. And then the posters that were presented in this session will be, those authors should also be available 11:45 through 12:45 local time as well, for poster session, as well as other posters. So I think with that, we'll wrap up our session. And Sung, do you have any other announcements to make?
No, you are covered all.
Okay, great. Well, thank you again for everyone. Look forward to seeing folks in person at the next Eastern Snow Conference or CGU CMOS meeting. And we'll keep the meeting open if we can. If the tech support could just keep the meeting open a little bit longer, if Richard can address those final questions. It looks like he's gotten to one of them, but that would be great. Thanks again, everyone.
Thanks, Eli.
Yeah, Richard, we've got our L-band system up and running and have tried deploying it on a helicopter with some success. So we should probably touch base about what you guys are working on and how we can maybe be more coordinated in sort of activities and lessons learned.